Case 3C, non-random aging, and Q is a Poisson pulse process. So let's explain what this means. We generalize case 3B here with aging. So we still have the Poisson occurrence of IID loads, the rate of occurrence being lambda. The loads are still independent of capacity, but the capacity is not time invariant. Aging is introduced for the first time in this problems involving Poisson loads, and it degrades according to a non-random function. So C of tau is C0 times D of tau, and D of tau is a non-random function. We make no restrictions that it has to be monotonic, and C0 is the initial capacity. The loads are Q1, Q2 up to Q of n, and this n is a Poisson random variable indicating the number of occurrences in the interval 0 to t. Each of these Q's is distributed according to FQ, and they are IID. So we start these discussions with the definition of the reliability function. R of t is the probability that Q1 is less than C0 dt1. Because we have aging now, we just can't write C0 every time. Q2 is less than C0 dt2, and Q3 is less than C0 dt3, and so on, all the way up to Qnt is less than C0 dtnt. The important point to note here is the presence of all those random variables t sub I. Those are capital letters T1, T2 all the way up to Tnt, and these are actually random variables. So we now have added quite new aspect of complexity in this problem. These occurrence times Ti, T1 up to Tnt, their values are random. At the same time, their number themselves is also random. So there is a random number of occurrence times which themselves are random. So we now have to restrict if we have to move forward. So we have to carefully condition and then remove the conditioning. Let's see how to do that. If we restrict the number of loads, if we condition capital N, then it gives us some simplification. So we bring in the theorem of total probability and express the probability, which is R, in terms of a partition of Nt. We have done this in the previous case also, so it should be known that we can condition the intersection of those events Q less than C on the number of occurrences, and then remove the conditioning by multiplying with the PMF of n and sum over all possible values of n. So that is the theorem of total probability applied on the number of Poisson occurrences. So that gives us at least some help that the number of t's are now known, small n. Now, once that happens, we are actually able to invoke a very useful theorem from the theory of point processes, Poisson processes, and that is that if we order these occurrence times, so if capital T1 is less than capital T2 all the way up to capital Tn, which is what we like, then the joint PDF of these occurrence times are actually jointly uniform, and that's a very helpful result. So f of the t vector, given that there are small n occurrences, is 1 over t to the power n. So that's basically 1 over t times 1 over t n times. So the length of the interval is t, which is from 0 to t, and multiplied n times gives us 1 over t to the power n. So this is something which we use and will be very helpful. So let's see what new things we have learned. In addition to what we had on the left panel, we'll add two more points there, that the t's are ordered and their conditional density, joint density, is 1 over t to the power n. Now we will proceed with what we had in the previous slide. So r of t is given as a sum of conditional probabilities multiplied by the respective PMFs. Now we can then condition on values of ti, the occurrence times. That would be the next thing we fix. So as soon as we do that, the q's being less than c's, that looks a little simpler. We have qi less than c0 dti for all i's, and that's going to be useful because that will let us bring in the CDF of the q's as soon as we are able to remove the randomness in C0 as well. So that's coming, but let's see what we have done here. So we have fixed the values of the occurrence times at arbitrary instance tau 1, tau 2 all the way up to tau n. N is the subscript small n. Now we bring in the total probability. We remove the conditioning on the t's, on the occurrence times, and that gives us an integration, all the n-dimensional integrations on the t's, where we bring in the conditional PDF of the occurrence times. So we again get back the unconditional reliability. But what we have gained here is that in the intersecting events q less than c, those we no longer have d of capital Ti, but d of tau I, and that is going to be helpful, as we will see in the next slide. So let's see what we can do from this point onward. So this is where we left in our previous slide. Now we can again condition the reliability on C0, the initial capacity. And as soon as we do that, we are in a position to bring in the CDF of the q's. So that's what you see in the last equation that you that's there on your screen, that we now have small c in the intersection events. So it's qi less than c d tau I, and that lets us bring in the CDF of q. So fq evaluated at c d tau I, and then bringing in the fact that the ft's are 1 over t, each of them. So we have a product of n of those terms. That gives us the sum of an integration to the power of n times the PMF of n. So that last term PMF of n has been with us from the beginning. That's what we are going to use next. So with this starting point, the conditional reliability of with C naught at an arbitrary value, by removing by bringing in the PMF of n, we are able to, as we did in case 3b, we are able to work through the sum and write the closed form solution as exponential of minus lambda t times 1 minus an integration. That integration makes use of the fact that C is no longer a time invariant property, but it can change due to aging. As long as that change is deterministic, it doesn't have to be monotonic one way or the other. So we can integrate the area under FQ C d tau from 0 to t, and then take its average over the interval, subtract that from 1, and what used to be exponential minus lambda t f bar q evaluated at c now has a much more complicated form. But if d was equal to 1, we would get back the same exact result of case 3b. Now our final step will be to remove the conditioning on C naught and give us a result that is evaluated as an expectation with respect to the random variable C naught. So if we are able to generate C naught by Monte Carlo simulations, then we would just need to evaluate that exponential that you see inside the kernel and take its average from a good number of samples, and then that would be an estimate of the reliability function.